Hello everyone. Today my presentation theme is enhancing multi-objective chaotic involution algorithm use an estimated convergence point. Today I will introduce my research about the evolutionary algorithm. There is today's speech topic. The first one is the research background and our motivation. The second is our proposal method. After that, we will talk about our research result, and in the end, we will talk about the conclusion and our future work. This page is our purpose of this research. We want to make a combine of multi-objective chaotic involution algorithm and estimated point. And after that, we test if the new algorithm will deliver better efficiency than the previous algorithm. Now, let me introduce the research background. Many problems in life consist of multiple conflicting goals. In many cases, when multiple targets exist in a particular area, at the same time, it becomes an evolutionary multi-objective optimization EMO problem. In general, the various goals of a multi-objective optimization problem often conflict. When we improve the performance of one objective, the performance of other objective is likely to be weakened. In other words, it is difficult to achieve optimal values for multiple purposes at the same time. In this page, I also want to introduce what is Pareto solution. The solution obtained by multi-objective optimization is generally called the Pareto solution. Like the picture in this page, if one solution's parameter is bigger than other solution in both F1 and F2 field, then we can say this one solution dominates the other solution. Like this picture, the point C dominates both A and B. This page is the original multi-objective chaos evolutionary algorithm. Multi-objective chaos optimization uses chaotic systems to explore the past and then use the non-dominated ranking to rank elements in the population with reference to crowding distance and tournament selection. This is the flow of the multi-objective chaos optimization algorithm. In this research, in order to improve the Pareto solution between generations, we proposed a method of optimizing the EMO search as the quantity of objective space by finding the estimated point where each movement vector intersects. Not only one goes during the experiment, but also the multi-objective chaos evolution optimization presented in this paper was useful. And this slide explains how the multi-objective chaos optimization algorithm works. In this page, I want to introduce chaos evolution. The basic principle of chaotic evolution, CE, is to simulate chaotic motion when generating new search points. This idea was inspired by some natural phenomena that can be probably modeled and explained by chaos systems, but deterministic models are not yet available. Therefore, we believe that chaotic systems can be used to simulate human evolution. The ergodic nature of the chaos system guarantees the feasibility and expression of chaos evolution. That is, the iterative variables of the systems can approach any position in the search space with arbitrary precision. The Q systems use equation 1, 2, and 3, and we set the crossover ratio of the equation 3 to 0.9. The logistatic map of the Q systems is shown in the equation 1. The map is a classic example of chaos caused by a simple non-linear equation, and shown in this picture, when mu equals 4, it fluctuates over the entire interval between 0 and 1. This slide is the estimated point of my research method. It can be derived from this generation sample and the previous generation sample to optimize the original result. In this picture, the yellow point A1 is the point of the original generation, and the blue point C1 is the point of this generation. Now we pair the blue and the yellow points with the smallest distance except 0. A plurality of points A and C become a vector B. When we extend B as a straight line, in the space where the vector converge, the point with the smallest distance to the line on which each vector is located is the estimated point, like the star in this picture. After getting the estimated point, we substitute the lowest rank point with this estimated point in the next generation. In this slide, I will show you how the estimated point working in this MOC algorithm. The blue arrow refers to where we use the estimated point. So after we intersect the vector, we use the method at the list page to find the estimated point, and we replace the point, which is the lowest rank, with the estimated point, and see whether the estimated convergence point can accelerate the algorithm. And now I will introduce the evolution and analysis method of the experiment to investigate the efficiency of our proposal. 5 multi-objective benchmark functions, the JDT 1, 2, 3, 4, and 6, are used in the experiment. We set the dimension of the function to 30 dimensions. Regarding the MOC algorithm, the number of individuals population size is 100 in all functions, and the number of generations is 1000. We test each algorithm for 30 trials running. To be fair, the initial parameters of each experiment are the same for all functions in the trial. We set the crossover rate to 0.9. The number and diversity of Paris solutions are two measurements of the EMO algorithm. To compare the performance of the MOC algorithm with or without the estimated points, results are evaluated using 4 metrics or methods. They are hypervolume metric, HV metric, general distance, GD, inverted general distance, IGD, and a statistical test. This slide, I will introduce the evaluation experiment. The hypervolume metric is the volume of the dimensional region of the target space surrounded by a set of non-dominated solutions, and reference points obtained by a multi-objective optimization algorithm. The general distance, GD, is the distance between the evaluated prepalette surface and the optimal prepalette surface. The inverted general distance, IGD, evaluates the convergence and variance performance of the algorithm by calculating the sum of minimum distance between the optimal parade front creepage points, evaluate parade front creepage points. And the significant test is a method used in scientific experiments to detect whether there is a difference between the experimental group and the control group and whether the difference is significant. Normally, only the maximum probability of creating the first type of array alpha is limited, and the probability of creating the second type of array beta is not considered. Such a hypothesis test is called a significance test, and the probability alpha is called a significance level. In statistics, events with a probability of less than 5% in the real world are usually called the impossible events, and conclusion error rates of less than 5% are considered significant difference in conclusion. After obtaining the performance metrics in this paper, we will test whether this index can indicate the result in a significant conclusion using Wilson sign ranking test. When the value of the significant size p-value is lower than 0.05, it is recognized as a significant result. This slide is the hypervalue of the JDT function, with the exception of the JDT4, which has a p-value greater than 0.05. The proposed method enables faster arithmetic up to the 30th generation. However, JDT2 does not reach the overlapping section in front of parade until the end, which may not look for a good point due to local convergence. This slide is the generational distance of the functions. In general distance GD, JDT2 and JDT3 can be found more non-dominated solutions by the proposed method up to the 30th generation. For JDT1 for 6, the parade solution indicates that the research range in the parameter space may be discrete. However, these three functions can search the parade front surface with a higher speed than the conventional method until the end. This slide is the inverted generational distance of JDT functions. For IGD, except JDT3 and JDT4 with p-values greater than 0.05, JDT2 collected more parade solutions before the first 20 generations. JDT6 GD is the same as the GD of JDT1 for 6. The search range of the parade solution in the variable space is considered to be discrete, but in the end, it finds the frontier faster than the conventional method. However, the result is doubtful for JDT1. As a result, it seems that the MOCE with an estimated convergence point outperforms the performance of the conventional algorithm. In this paper, we applied a method that constructs an estimated point where each motion vector intersects and use in this estimated point to enhance the search capability of the multi-objective chaotic evolution algorithm. By comparing the conventional method and the proposed method, the multi-objective chaotic involution, or estimated point plus multi-objective chaotic involution. We find that the proposal using an estimated convergence point is effective for multi-objective optimization problem in complex problem. We found there is not much efficiency in low-dimensional problems because the regional level of the Pareto frontier is not complicated. So how to optimize the simple problems which our proposal is a research subject in the future? We need to further investigate MOCE that contains the estimated point for a variety of multi-objective optimization problems, including real-world ones. This open topic and the potential research subjects will be involved in our future work. So that's all for my presentation. So thank you for listening.